Okay, so welcome back to your module 1 again. Okay, so this is now your last unit of simple stresses, which is what we call as the thin-walled pressure vessels, okay, or just simply thin-walled pressure. So, okay, in this unit, these are our unit learning outcomes to compute for what we call as tangential stress and then compute for what we call as the longitudinal stress. So we will later on define what are these, okay. So, but first, let's try to understand what is thin-walled pressure vessels, okay? So, in Unit 1, we examined various cases involving uniform normal stresses acting in bars, okay? So, that could be a compressive stress or that could be a tensile stress, okay? So, the area there is perpendicular, okay? So, that is actually what we will be using here. This thin-walled pressure is a normal stress, but it is now called into a specific name, which is thin-walled pressure, because that is the type of normal stress that we can figure out on, or that we can find on the thin-walled pressure vessels, okay? But it is still a normal stress, okay? So another application of uniformly distributed normal stress occurs in the approximate analysis of thin-walled pressure. So that is for us to simplify the analysis by considering it to be a normal stress. We will later on find that out. We will go to the figure. Okay, so such as cylindrical, spherical, conical, toroidal shells subjected to internal or external pressures from a gas or liquid. So as long as that is, there is what we call as these bursting pressures that is handled by this thin wall, then that can categorized under this thin-walled pressure, okay? Let's go. Okay. So liquid and gas storage tanks and containers, water pipes, boilers, submarine hulls, and certain airplane components are common examples of thin-walled pressure vessels. So again, there are a lot of that. And then a tank or pipe carrying a fluid or gas under pressure is subjected to tensile force, okay, while resisting bursting, developed across longitudinal and transverse sections. Okay, so that is what I'm saying. The type of load or the type of force handled by these thin-walled vessels is what we call as the bursting pressure. Bursting pressure in a way because that is trying to force the material outwards in any direction. So that's why we call it bursting pressure. Okay, so let's try to analyze this type of pressure, okay? So that will be categorized in two, okay? In two different types of these thin-walled pressures, okay? First is the tangential stress, and then second is the longitudinal stress. So if you say tangential, that could be called as the circumferential stress, or if you say longitudinal, that could be called as the axial. So if you will try to look at the scenario of the axial, that is almost the same as our normal, isn't it? Only that we are now having this one under a thin-walled pressure, or I mean under a thin-walled vessel. So we call this one a thin-walled pressure. But that is still another type, or that is still a normal pressure or a normal stress. Okay? So look at this. The area, if I will try to cut, that is a thin wall. Let's say this is a pipe. This is a part of the pipe. There are two division of, or we can divide the stress handled by this pipe within two. It could be the tangential and longitudinal. So this is the first type of stress handled by that pipe. Okay, so that is the stress within the circumference of the circle, or within the circumference, or within the wall itself. Okay, so following the shape of the circle. So within this area, okay, that is the stress. Let's put that one as sigma, since that is a normal stress, but let's put it as sub h. The h, or actually later on, no, that is only in the figure, but later on we can put that one as sigma sub t. It means tangential. And then later on this one, sigma sub l, but that is just in the figure, okay, since this is a ready-made figure that I only used, okay, that we only used. But we will use this one as sigma sub t, sigma sub l. T stands for tangential, L stands for longitudinal. Okay, so we have other direction of stress being experienced by the pipe. It is along its length. Let's say this is the length. Okay, it could be the stress within the circumference, or it could be the stress along the length. So this is the other stress experienced by the thin wall, which is, we can call it longitudinal since it is in the direction of its length. Okay, circumferential because it is in the circumference, within the circumference of the circle. Okay, so those are the two types of the thin walled stresses. So first, the question there is, how are we going to find out this force that is exerting an effort for us to have this tangential stress and then for us to have this longitudinal stress? That is what we call as the bursting pressure P. Okay, bursting pressure P. That is the pressure due to the, it depends, whatever is inside, whatever is contained by that thin wall. Okay, it could be a water or a liquid, or it could be a gas, or if that is a tank of, let's say we are talking about a what do you call this one, a gas tank, then that could be a gas. Okay, or it could be a liquid, and so on and so forth. So as long as that is exerting a bursting pressure in any direction, okay, that is how a water or a liquid and gas will spread. Okay, it is in all the directions. So the pressure is exerted in all the directions. So we call this one a bursting pressure. So consider the tank being subjected to an internal pressure P, or that is a bursting pressure P, okay, in any direction. And then the length of the tank is L, so that is the length of this tank. And then the wall thickness, let's say that is T, okay. And then isolating the right half of the tank, if I will try to cut that, then that will be this part, okay, the right side. Note that the resultant vertical force due to the pressure P. Okay, if you say pressure, that is same as stress. Okay, because stress is actually a pressure. If you say pressure, that is intensity of load per area, over area. Is it, you recall your physics? That is a pressure. The, again, force is distributed within the area. We only call this one stress if we are now referring to the material itself. Okay, but if you are just focusing on the force, okay, and the external force, then that is the pressure. So again, pressure, let's say that is the force P, small force P, is a force over area, isn't it? So what is the unit of that? That is, it's either in Newton per mm squared or megapascal, or Newton per meter squared Pascal. So that is our force P. Okay, and if I want to, this is what is given to us, the bursting pressure. If I want to get that force F, because that is what I need to compute these stresses, okay, then I can figure this out. I can rearrange this one, and then you will have there the force F cross multiply the pressure P, small p, and the area of whatever is under that force F, whatever that area, then that will be the one to be converted into a single force, or concentrated force F. Okay, so that area, if you are using MPa, you need to have that area in millimeters. Okay, so that is just unit manipulation. So again, that is how we ended up here with F, which is P over A. So the pressure, if I will cut this one, is in any direction, but we can consider this rectangular, which is considered to be uniform force pressure P, and then multiply that one with the area, which is under that pressure P. So this, what is that area? Okay, that is due to the diameter, since I cut that one at the middle, exactly at the middle. Why? Because yes, I can cut it within this one, this any part of that circle, but the maximum that we can have is within the middle or the center. So cut that one. What is the area? The largest area that will handle that pressure P is your middle, which will be the dimension diameter. By the way, if we say diameter, here in thin wall, we are referring to the inside diameter of the tank or the vessel. Okay, inside diameter. And then, so that is the area, D times the length, which is exactly the same as the length of the tank itself. Okay, so that is that is the area, D times L. So pressure P whatever that value that will be given on a certain problem, then you can calculate the force F, which is handled by this thin wall. Okay, that is the equivalent force being carried by that wall. Okay, since I cut this one exactly in half, I will expose there two areas: the area of the wall on the top and the area of the wall here below. Okay, so you have two areas. Therefore, the force F will be divided into equal two parts, which is equivalent to T. Or we can say by a summation of forces horizontal, you can say that force F is equivalent to twice T. Okay, so if what is F? That is pressure P times dl. And then what is your 2 times T? That is a normal force. I mean normal stress, isn't it? I mean normal force to the area, which is the wall, cut area of the wall. So T there, where will I get the T? That is the question. The T, I will get that one from the strength of the stress of the normal to the area, okay, which is cut to the wall. So what is the normal strength there, or I mean normal stress there? Okay, you can start again for within the sigma is equal to P over A. Cross multiply your sigma, you will end up with A there, and then T is equal to, okay, that is the T, the force here, which is sigma T times area of the wall, which is the area of the wall will be T times, okay, what is the area of this wall, one of the cut here, the length of that times the thickness, that is the area of one of these. So that force T is equivalent to sigma T, which is actually, we call this one we put the sub T, it means that is tangential, but that is still a normal stress. Okay, so whatever that normal stress sigma sub T, multiply that one with the area, which is the thickness times the length, area of one of the cut here, then that is the force T. Then satisfying this equation, multiply that by 2, since there are two parts of that vessel experiencing the same stress, then you can equate and then play around with that. You will have that sigma T. Okay, so sigma T, okay, that is the tangential stress of the vessel, and which is thin walled, okay, under force P or pressure P. So okay, we just play around with this. This will go down, L and L cancels. Okay, so there is no effect actually of that L. We only use that for derivation. So within any length of that tank, this tangential stress is still the same as long as that force P is constant. Okay, so L cancels. You will end up with pressure P times D, the diameter, inside diameter, divided by the twice T. Okay, T is the thickness, wall thickness. So that is our sigma T. So in case you forgot about this formula, you can always derive that one using this figure. Okay, wherein the force being handled is the equivalent force F. If I will cut this one, okay, convert that pressure that is found here into a uniform or into a concentrated load, and divide it by 2. That is the one handled by each of the area. And then using our formula, of course, for normal stress, since again tangential stress is a normal stress, you can figure out later on the formula of your tangential stress in case you forgot about this. Okay, let's proceed to your longitudinal stress. So consider the free body diagram in the transverse section of the tank. So let's now consider we will cut that one perpendicular to the length. Okay, we will expose the area handling the force which is parallel to your length. Okay, so the total force acting at the rear of the tank, which is force F, must equal to the total longitudinal stress on the wall T. Okay, that is equilibrium. Okay, that should be equal. And then since T is so small compared to D, the area of the wall is close to pi dt. Okay, supposedly, okay, if you try to look here, supposedly you're referring to the area of that in case, okay, the area of the big circle subtract the area of the small circle. If you're referring here to a big thickness, okay, big thickness. But since the thickness is just small, the thickness is very, very small compared to the diameter, of course. Okay, in ratio to diameter, this thickness is very, very small. This thickness T is very, very small. So R1, R2. So if I will subtract that R1, R2, that is a very, very small thickness, which is common on thin wall. That's why we call this one thin wall vessels. So supposedly, how to get this area here, since that is the area handling the force, isn't it? Longitudinal force. That should be the area. So supposedly, how we will compute that is area of the big circle minus area of the space. However, to make it simpler, okay, which is this is adapted by most of the computations. Even if you try to open other books, this is adapted, okay. But supposedly the exact computation is that area of the big circle minus area of the space. However, to simplify that one, we can cut this one and then spread that one as a rectangle, as a plain rectangle, okay. We can cut this one in half and then spread into a single rectangle which has a dimension of T, and what is this? The circumference of the circle. Isn't it? Just like what I explained before in one of our example in your normal stress. Okay. However, in here, the thickness is very, very small in a thin wall pressure vessels. The thickness is very, very small. So this is how we will compute this one. Okay. So 2 pi r if you are using the radius, but since we are commonly using the diameter, which is the inside diameter, that is equivalent to pi d. Sorry, that is not 2, that is pi d. Okay, so that is the dimension. So the area handling that force, which is to the axis, along the axis, this is the area which is length pi d times thickness. Okay, so that is the area handling that one. Okay, so going back here in this figure, the area handling that force T, which is the equivalent of force F, is pi d times T. Again, that is where we get this one. How about this F? Just like how my explanation a while ago, we will convert that pressure P. Okay, we will convert that pressure P into a concentrated force F. So for us to make that as a force, multiply the area covered by that pressure P. So what is the area? That is the circle here. Okay, experiencing that distributed bursting pressure P. So what is the area? That is area of a circle, pi over 4 d squared. So that is multiplied to your pressure P. You will end up with the concentrated load F. That is due to the pressure of the liquid or the gas inside. And then that is to be handled, to be reacted, or that will be supported by your T, or equated by the T, because of the support of your, for that not to burst, that should be handled by your area here. Okay, which is we can equate that force F as T, which is that T is a product of the stress on this area and then the handling area, which is I explained here, pi d times T. Pi d times T. That is the longitudinal stress. Okay, that is now your longitudinal stress. That is the stress within the length of the pipe. Okay, so equate this one so that you will find out, we will figure out the formula for this. Equate. So this one, T, that is your T. Sigma sub L pi d dt, pi dt is equal to pressure P pi over 4 d squared. So one of the d cancels. 4 will remain below, pi and pi cancels, okay, T will go down. So you will end up here with sigma L as your pressure P times D over 4T. If you try to go back to your tangential, that is your longitudinal, okay? Go back to tangential, that is PD over 2T. For longitudinal, that is PD over 4T. So what do you notice? Okay, if I will try to divide, or if I will try to multiply this by 2, if I will to multiply your longitudinal stress by 2, okay, multiply that by 2, so 2 and 4 cancels, you will be left here with 2 below. That will be exactly the same as your tangential stress. Therefore, to relate this longitudinal and tangential stress, the tangential is equivalent to twice the longitudinal. Okay. Okay. So that is the relationship of the tangential and longitudinal. The tangential is twice the longitudinal stress. So again, which one is more stress? The tangential. Okay. The circumference is more stress than the length. Okay. So again, that's the relationship. Okay. So those are our formulas. Okay. Let's have an example. So a cylindrical steel pressure vessel 400 millimeter in diameter. Okay. So this is the vessel which is 400 in diameter. That is again, if you say diameter D, that is always inside diameter. If we are referring to the tank. And with a wall thickness of 20 millimeters. So thickness of that wall, of this wall, okay, this is already cut into parts for us to expose the dimensions. Thickness of this and the thickness of the cover is both 20 millimeter and is subjected to internal pressure. So that this is your bursting pressure P, which is 4.5 meganewton per meter squared, or this is megapascal. Actually, this is megapascal. Okay, this is the other form of unit of megapascal instead from that the Newton per millimeter squared. Okay, now calculate. Supposedly that should be no A since there is only one unknown. So calculate the tangential and longitudinal stress on the steel. Okay, steel pressure vessel. So let's start with these are the formulas which we derived a while ago. Tangential is PD over 2T, longitudinal is PD over 4T. Okay, so write down the given, and then required is the tangential and longitudinal. So we can start by, okay, actually this is for you to be again to recall the derivation, but since we already derived that, we can use it directly. Okay, but in case you forgot, this is again where you will start. Okay, deriving your equations. So tangential is PD over 2T. Your pressure, bursting pressure, which is in megapascal, is 4.5 times the diameter, which should be in millimeter. If you are using the Newton per millimeter squared, you should be using the length, which is in millimeter. So the diameter of that is the big D, which is the diameter is 400 millimeter, and then the thickness is 20 millimeters. So you will end up here with calculating this as 45 megapascal, exactly 45 megapascal. Okay, calculate now the longitudinal. So that is, again, this is the derivation for that. So we will just use this directly. PD over 4T. So P is the same, D is the same, only that T is the same, only that that is 4. So multiply that one and divide, you will end up with 22.5, which is actually, again, if you will relate this one, the tangential is twice. If I will multiply this by 2, that is exactly 45. Okay, so that is your tangential and longitudinal stress of our thin pressure vessel, cylindrical shape. Okay. So let's have one more. So a cylindrical pressure vessel is fabricated from steel plate that has a thickness of 20 millimeters. The diameter of the pressure vessel is 450 millimeter and its length is 2 meters. Determine the maximum internal pressure that can be applied if the longitudinal stress is limited to 140, or it means that is the strength. Okay, the strength of the metal used with respect to longitudinal stress, and the circumferential stress is limited. It means that is we will limit ourselves up to 60 megapascal. So it means that is the strength of that metal in terms of tangential stress. Okay, so now it is the other way around. What is given is this allowable stresses or limit of these stresses, and then what we are going to figure out is the maximum pressure P, or that is the bursting pressure P. So again, we will start this again. These are again the derivations, so we can use that directly since we already derived, but in case you forgot, this is how you will start. Okay, so by the way, okay, for you not to be confused, this our derivation is based on circle shape or cylindrical shape, but there are other containers wherein the shape is rectangle, square, or other shapes. So the formula will be different. But you can always start on the way we derive this one. Okay, cut at the middle where you will find the maximum pressure, and then get equivalent force, and then divide that one by the area handling. So the same concept. So again, that is of course that will maybe for your own to figure it out also. Apply what you learn here on the other shape of these tanks. Okay, so in our case we focused on cylindrical because that is what we derived. But in case again your cross section is different, then it means that this is not applicable, because in the first place, if that is rectangle, there is no diameter for rectangle. Okay. Okay, so we will use directly. So sigma t, that is given for, let's focus first on tangential. So we will limit ourselves with a stress of 60 megapascal. That is the strength in terms of tangential stress. So PD, that P is the unknown, diameter of that is 450. Okay. 2, and then T there, the thickness of that is 20 millimeters. And then substitute. Okay, by the way, sorry, let me just change these units here. Okay, so going back to our solution, I just changed the units. Okay, I just changed the units for you not to be confused. So again, your 60 is the megapascal, so I can write that directly as Newton per millimeter squared, so that I will be using millimeter units for the distances or lengths, or thickness, or the diameter. Okay, so 60 Newton per millimeter squared. That is equal to force P, that is the unknown, times the diameter 450, all over 2 times the thickness 20. So cross multiply. By the way, this mm and mm cancels. So this number, if I will cross multiply that, will be unitless. Therefore, your force P will still be in megapascal. Okay, so that will still be in megapascal. So calculating that one, 60. Okay, let me just check. 60 times 2 times 20 divided by 450, you will end up with 16 over 3, or that is 5.33 megapascal. So that is how much bursting pressure your tangential tangential stress can handle. Okay, this circumference can handle. That is the meaning of that. Then let's try to find out how much of that bursting pressure that longitudinal can handle. So we will go to the formula PD over 40, substitute the same thing, but this time the stress is 140. Okay, the material is a little bit stronger longitudinally compared to tangential, maybe because actually this is a single type of material. Of course, that should be. So the strength should be the same, isn't it? That this is being pulled. The circumferential is also a tensile, and so with the longitudinal, it is also tangential. I mean, it is also tensile. But why is it that the strength are different? Maybe because the strength of the steel, or the steel, since that is steel plate, okay, the strength of the steel is reduced when in circumferential, because maybe due to bending. Okay, originally, if that is not bended, then the strength in any direction of tensile stress will be the same. But since that is bended, maybe the strength will be reduced. So that is according to the problem. Okay, 60 megapascal only. So that is according to the problem. But supposedly, the strength of the entire plate will be the same. However, because maybe due to bending, that will reduce the strength circumferential of this steel. Okay, steel plate. Okay, so 140, that is 140 megapascal, substitute. So all I need to do is change 1 to 4, and then 140. You will end up there with 2 to 4 over 9, or that is 24.89 megapascal. So that is how much this tangential or the circle can handle. 5.33 megapascal only, bursting pressure of 5.33, but the longitudinal part of the tank can handle 24.89. So what does that mean? All in all, what can the entire vessel handle is the smallest. Okay, because as I will surpass this 5.23 going to the 24.89, your tangent or your circle, your circumference will already fail. Even if your longitudinal will not yet fail, because that can carry up to 24.89, but once I will surpass that P, which is 5.33, then your circumferential will fail already. So the entire vessel will fail. Therefore, the maximum that it can carry will be 5.33 megapascal. Okay? So, okay, to end our discussion for this bearing, let's try to recall some important concepts. So, tangential stress is twice that of the longitudinal stress for cylindrical. Okay, this is only for cylindrical since that is what we derived. Okay, so pressure has the same unit as stress. Okay, just this is what I am saying, explaining, and actually this is discussed in your physics. And then the inside diameter is used since mostly of the problem that is the given. Okay, so that ends our unit 4 of module 1, and at the same time the entire module 1, since this is the end topic of your simple stresses. So recall, let's try to recall again the 4 units. First one, normal stress, when the area is perpendicular to the force. Second is shearing stress or shear stress, when the area is parallel to the force. Unit 3 is bearing stress, that is due to the contact of two different bodies. And the area that we are using is always the projected area. Okay, projected area. And then last one is the thin wall pressure. That is just a special scenario of your normal stress. Since in your thin wall pressure, these are all normal stresses. Okay, these are all tensile stresses. So that is just a type of normal stress, but intended for a thin walled vessels. So again, what we derived here is a thin-walled vessel in the shape of cylinder. But if you will later on solve for another cross-section, let's say square rectangle, then you need to derive your own formula, just like what we did in this unit 4. Okay, so if you have any question, you can comment that below the discussion, or we will be discussing this live. Okay, so thank you very much for watching.